For more than 50 years, the question of why humanity never returned to the moon after Apollo has lingered, whispered in classrooms, debated in obscure forums, and quietly studied in laboratories far from Houston. The official explanations point to politics, budgets, and shifting national priorities, saying that attention moved from lunar exploration to low Earth orbit operations like the Space Shuttle and the International Space Station. But viewed through the eyes of scientists abroad, particularly in China, a very different picture emerges. One marked not only by financial constraints, but by engineering gaps, fading technical memory, and environmental truths more hostile than we once understood. Their perspective frames the silence not as something suspicious, but as something sobering. The moon does not forgive second chances, and when Apollo 17's crew left the lunar surface in December 1972, they left behind not just footprints, but an entire ecosystem of technical expertise that rapidly dissolved once the program ended. The lunar hardware became museum pieces, contracts dissolved, and the workforce that built an era dispersed. As the historical narrative often explains, the United States simply shifted focus. Yet beneath that tidy story lies a deeper tale. The erosion of capability occurring silently over decades, the slow decay of know-how, the fragility of systems built for a brief period of intense national focus. When examined through technical reports and commentary, especially those produced by Chinese researchers analyzing the U.S. lunar program from afar, it becomes clear that the real challenge was not only a matter of lost funding, but of atrophied capability. The spacecraft and systems that carried humans to the moon during Apollo were suited for narrow operational envelopes. They worked, but they were not easily reproducible, and once the hardware was retired, much of the tacit knowledge vanished with it. For international observers, the absence of a return to the moon for half a century suggests not a lack of ambition, but a recognition that the moon remains an environment unlike any other. Its radiation, surface hazards, re-entry velocities, and unforgiving physics have not softened over time. If anything, our awareness of their complexity has deepened. And when NASA finally attempted to rekindle lunar exploration through the Artemis program, it encountered realities that forced hard pauses. The most striking example came after Artemis I in 2022, when the Orion spacecraft's heat shield, made of reformulated Avcoat material descended from Apollo, behaved unexpectedly during reentry. Instead of ablating smoothly, it flaked in unpredictable chunks as pockets of superheated plasma penetrated its surface layers. This was no minor cosmetic flaw. It was a mission-critical issue requiring NASA to delay Artemis II, originally expected in 2024, then in 2025, and now pushed to 2026, with Artemis III drifting even further beyond. The incident underscored a truth often overshadowed by nostalgia. Returning from lunar distances is not simply Apollo with better computers. It is a fundamentally different arena of thermodynamics and material stress, one we have not confronted in human spaceflight for 50 years. But thermal extremes are only one invisible barrier. Radiation remains an even quieter threat, silent, persistent, and far more deadly outside Earth's magnetosphere. Apollo astronauts spent brief windows in deep space. Artemis missions will last much longer. That difference alone transforms risk profiles dramatically, especially now, during the heightened activity of solar cycle 25, peaking around 2025. Chinese and European analyses emphasize that shielding cannot simply be thickened. Its effectiveness depends on distribution, orientation, timing, and a spacecraft's dynamic relationship with the solar environment. Artemis mission planning must now incorporate solar forecasting, onboard particle monitoring, and designated storm shelters inside the crew module. Radiation, unlike heat, offers no visual cue, no sound, no moment of drama. It builds quietly and inexorably. As mission durations increase, so does the need for protective strategies far more sophisticated than anything Apollo required. Even the moon's surface, so still from afar, presents hazards that were only partly understood in the 20th century. Lunar dust, or regolith, is nothing like Earth's sand or soil. Formed by billions of years of micrometeorite impacts in a vacuum, never rounded by wind or water, its particles are jagged, glass-like, electrostatically charged, and razor-sharp at the microscopic level. Apollo astronauts reported it clinging like glue-coated sandpaper, scratching visors, infiltrating seals, and irritating eyes and lungs. Chinese analyses of regolith samples from Chang'e missions confirm its abrasive, semi-reactive nature. Dust mitigation is not a minor engineering concern. It affects airlocks, filtration, suit integrity, bearings, and the longevity of surface equipment. On long-duration missions, dust becomes one of the quiet but relentless threats, one that compounds daily until it jeopardizes operations. Beneath the dust, the moon's interior presents additional obstacles. Gravitational anomalies. Mascons can distort trajectories during descent, complicating landings especially near the South Pole, where Artemis 3 aims to go. Meanwhile, moonquakes, which last far longer than terrestrial quakes due to the moon's rigid, dry crust, pose risks to habitats and infrastructure. Data from Apollo seismometers, which shut down in 1977, offered early warnings, but half a century without seismic monitoring leaves major gaps in understanding how the lunar surface behaves. Chinese researchers studying Chang'e lander data have stressed that we stopped listening too soon. Any long-term lunar presence requires a renewed focus on seismic and gravitational modeling. Against this backdrop of physical challenges lies the political and economic dimension. But even that is more complicated than the usual narrative suggests. It is tempting to say the U.S. did not return to the moon simply because public interest waned and budgets tightened after Apollo. But Chinese aerospace analysts argue that the deeper issue was not financial, but structural. Technological memory decays rapidly when systems are abandoned. From 1975 to 2010, nearly all lunar-rated hardware was shelved. Saturn V tooling was scrapped. Lander design and production capability evaporated. Engineers retired. Supply chains dissolved. Even documentation, drawings, test reports, materials data became fragmented or lost. Thus, Artemis was not a continuation of Apollo, but a resurrection of a forgotten architecture. Rebuilding lost capability is harder than inventing something new from scratch, Chinese analysts note, because legacy systems come with outdated assumptions, defunct suppliers, and the need to revalidate everything in modern contexts. When Artemis stumbled due to heat shield behavior, the delays were not signs of weakness, but signs of a program forced to relearn lessons buried for decades. From China's perspective, the silence surrounding certain details of Artemis delays is not interpreted as secrecy, but as a sign of complexity. Their own lunar program, with the Chang'e series and the emerging International Lunar Research Station, emphasizes incremental progress, transparent technical reporting, and exhaustive testing. They see the U.S. delays not as failures, but as evidence of the immense difficulty of returning to the moon sustainably. If the issues were simple, the fixes would be quick. When delays grow, they assume the underlying challenges are deep. This interpretation is not conspiratorial. It is an acknowledgement that engineering gaps and knowledge loss cannot be remedied overnight. Their critique is subtle. Returning to the moon is not about proving capability, but about preserving and evolving it. What stalled after Apollo was not interest, but continuity. The collapse of the Apollo-era engineering pipeline illustrates this. After 1972, the infrastructure that supported human lunar exploration dissolved. When NASA began the Artemis initiative, it faced not a dormant system, but an extinct one. Skills such as producing lunar-rated life support systems, precision-engineered landers, or deep space avionics had to be rebuilt almost from nothing. Contractors had to relearn tolerances abandoned decades prior. Some materials used in Apollo were no longer manufactured. Modernizing outdated designs required reverse engineering from incomplete archives. Chinese engineers studying the U.S. experience described this process as technical archaeology, uncovering, reconstructing, and validating methods from a bygone era while adapting them to modern standards. Artemis is therefore slow not because NASA lacks ambition, but because the task is equivalent to reviving an ancient industry while simultaneously inventing its future. This context reframes the delay question. Artemis delays are not bureaucratic foot-dragging. They are the result of confronting unforgiving physical reality